Okay, the last topic I want to cover here is the idea of doing feedback design along trajectories. Okay, so the trajectory optimization gives us some open loop tape, right? Tape, like a recording of an input U of t. Okay, but there's basically, in order to execute this on a real robot, you somehow need to make it robust. You need to somehow stabilize this, right? So the word trajectory stabilization is often used. I want to be a little careful with that because technically stability only happens as time goes to infinity, so a finite trajectory can't actually be stable, but you'll recognize this in the literature sometimes called trajectory stabilization. And it turns out you can do it with LQR. Okay, so far what we did in LQR is we stabilized a nominal point, right? So we wrote we said that x bar is just x minus some nominal operating point. U bar was u minus some nominal operating point, right? And then we could write down the dynamics of our system with the Taylor expansion as a linear system in this new coordinates, the relative coordinates. And then we minimized, we could solve the sort of LQR problem to minimize over u some quadratic cost function. We did infinite horizon. Okay, so it turns out magically that this extends very easily to the case of a trajectory. So here's what's going to be different. Now we're going to linearize along the trajectory, which sounds like a funny thing, but it's not that bad. So now we have x bar is whatever my x is minus x0 of t. So I've got a nominal trajectory. Similarly, u bar, which these are always a function of time, right, is whatever my current u is, but its difference from the nominal trajectory u0 t. Okay, when I go to then take the Taylor expansion of this, now my coordinates are time dependent, and what I end up with is x bar dot is a time varying x bar of t bt u bar of t. Okay, the Taylor expansion, exactly like we did before, gives me something almost identical, but now my A and B matrices are a function of time. Okay. Similarly, we're going to be able to we're going to write a slightly modified cost function. We want to somehow minimize over u just over my finite trajectory x bar of t. Now q of t, we're allowed to make it time varying if we'd like. Same with r. Now the same conditions are as before. We're always going to make same down here for all t. Where q has to be semi-definite and r has to be positive definite. Okay. It turns out that even though this looks scary, if you think about this, this is a very broad class of systems, the linear time varying systems. time varying linear system, and a time varying cost. Surprisingly, the same math we did in the derivation of LQR plays out just fine in this time varying case. Let's see how that looks. Okay, so now remember, if we before we had guessed magically that x transpose s of x was our cost to go. Now we're going to just do almost exactly the same thing. We're going to say our cost to go is now x transpose s of t x for our cost to go. Now these are bars, but I'm going to drop the bars for the remainder of this slide just to save myself some writing. All of the LQR is going to be in the local coordinates. Okay. And similar, we're still going to have s of t equals s of t greater than 0. Okay. Now if we write the Hamilton-Jacobi with this, we're going to, if we write 0 equals min over u, g of x u, is partial j partial x, f of x u. Now for a time varying cost to go, there's one more term we have to capture in our HBJ. Like this. This is the Hamilton-Jacobi-Bellman equation for the time varying case. Turns out if you pop in our cost function, we write in you take the derivatives, we stick in a of t, x of t, plus b of t, u of t. You'll do the same thing. You'll take the derivative with respect to u of that whole thing, set it equal to 0, and you're going to find that now u of t is just some time varying negative r inverse t b transpose t s of t x of t. And if you insert it back into the original equation, what you get out is plus one extra term. Okay, so this was the algebraic Riccati equation. From LQR. This now is a new term for the time dependence. And the result is called the differential Riccati equation. And you really should think of this as a dynamical system, a differential equation, where negative s dot of time equals this whole thing, q minus s, b r inverse, b transpose s. Okay? This is exactly a differential equation that describes the solution of the optimal cost to go. The way I've written it, the problem formulation, we actually have final conditions, t final, because s final is just 0, because I don't have any final cost. If I were to put a final cost in, I might have a non-zero solution here. Okay, so I can actually solve the LQR problem by differentiating backwards in time my differential Riccati equation it will find an S. There's a unique positive definite S solution that will give me the cost to go here, which satisfies the Bellman equation. Okay, what does that mean for you? For a user, what that means is you have to design the LQR controller. You simply have to integrate backwards over the trajectory to get my cost to go, and then my controller is just negative kt xt. This is u bar, okay, right? U bar of t equals negative kt x bar of t. Okay, you can just extract it once you have s. It's just a simple function of s. Okay, I'm going to show you in a second that this works very well. Now, it's not quite as mainstream as LQR. It doesn't exist as a function in MATLAB, but it is a function in Drake, and you can just call TV LQR in Drake. And you give it the dynamical system, and it'll compute K of t and S of t, just in case you want it.